So this is gearing up for section 4.1, where you have the analogy or the equation with electrical flow. And you often think of these things in the analogy of water flow, right? Whereas some of the big things are where your current I is a lot like the current of water. When you come across one of those jagged symbols, it implies that you have a resistor here, which you might imagine as a pipe squeezing a little bit, an inductance, something that seems more or less keep the flow going, sort of like a turbine or a fan. And then over here, if there's a capacitor, it's often thought of like a diaphragm or something of the sort. In the physical situation here, a capacitor is often some sort of gap or place that really builds up an electric charge. So we're asked for particular, I'm looking at problem number 57 here, and in problem 57 from section 4.1, it asks us the following. It says we have a circuit that looks sort of like this, with a resistor, like so, and we have this system that says, well, it has some voltage when t is less than 0, but as soon as time begins for our clock, you're not putting any sort of voltage into this. So what do we expect to happen? Well, we have some resistor here, and we're not adding anything to it, so it's probably going to die down. You know, when you have a capacitor, that's often something that you might expect a little bit of an oscillation back and forth, sort of like in the water analogy of some sort of diaphragm that pushes back and forth. You'd expect it to go to 0. Part B says, for a time greater than 0, we want to use the voltage law to determine the sum of the voltage drops around the circuit. It says set it equal to 0 to obtain a first-order differential equation involving R, I dot, L, and I, and determine the initial conditions. So using that, looking at this problem here, if you recall from what we saw right up above, let me scroll up there for a second. When you have the resistor, you often would add R times I, right? So that's when you have a resistor. When we have an inductor here, we would add L, right, times I dot. So let's write that down here. So we're expecting, we have L times I dot. I'm going to write that first, just so we have the derivative showing up first, plus R I, and that's going to be equal to 0, since we're not going to be plugging in any voltage values, right? Because this is what we call a homogeneous equation. So we have this. Now what is our initial condition? So our initial condition that we're looking for is, well, what is our current at time equaling 0? So our current, when time is 0, you might think about just, well, what was, excuse me, I just changed the size of my screen there. The voltage at time 0, we're also going to consider that we have some resistance in there. The next part of this problem just asks us to solve this. And so notice I'm going to rewrite it like maybe something that looks a little bit more familiar. Dividing everything by L, since it's just a constant, is equal to 0. So this should be going, way back. We don't even have any sort of oscillation, right? Because there's no second derivative. And so this is really just, can be written, or call this one, I dot is equal to negative. So this is way back to one of the first differential equations we solved, right? Where something, when you take a derivative of it, it's equal to what it was before, times negative RL. Well, this is just going to say then that I is equal to, we have some constant, right, we're not sure what it is yet, times E to the negative R over L times T. So then in order to find the constant, we just have to plug in our initial condition. So I of 0, right, is equal to V naught over R. Well, that's just going to be equal to C. So that gives you your final solution as I is equal to V naught over R negative RL times T. Great. And then part D, excuse me, I lost my page. Part D asks that we use the values. All right, so part D. Value R is equal to 40 ohms. L is equal to 5 henries. And the initial voltage here is 10 volts. And we want to use those values to obtain an explicit solution. So it's really just asking us to plug in those values to the solution we had before. So maybe I'll do this in a different color. Say here then that your current is going to be, well, 10 divided by 40, so 1/4. D, 40 divided by 5 is negative 8T. And this is finally measured in ohms. All right, great.